All right. I suggest that we start. Good day, everyone. Thank you all for coming. Our today's speaker is Dmitry Dylov, who is the head of the Computational Imaging Laboratory at Skoltech. And today, Dmitry will talk about physics-inspired imaging principles for the benefit of computer vision. Dmitry, please.
Hello, everyone. Thank you for the introduction and for the invitation to describe what we're doing in Computational Imaging Laboratory at Skoltech. I'm associate professor there. The group is about 20 people right now. And the core of our research is devoted to something that we borrow from physics and the mathematics of image formation. Today, with the hype of diffusion models, you don't really have to motivate reconsidering physics anymore because everyone appreciates the physical modeling and statistical principles that go into the modern probabilistic modeling. But today, I will describe some of the heuristic methods that are also borrowed from physics and use the analogy of image formation and several image formation principles that actually can help you solve your computer vision task. This is two directions, probably major directions in the group. And I'm not talking about fundamental aspects today, but I will talk about medical vision quite a bit, because this is our main adopter of our technology as far as applications go. So I usually start my pitch with a simple question. If you have a camera and it captures this picture of this dog, this is my dog, and imagine you have an image like that. What is the mathematical operation that's responsible for formation of this image? And I don't know if we have that voting or any polls in this particular Zoom, but the correct answer is convolution. It's not multiplication, not addition, as many would think. It's actually convolution. And if you want to learn a little bit more details about that, you essentially have an ideal underlying image which is ruined by the imperfection, the optical imperfections of the lens that you're using, as well as other aberrations and distortions that exist in imaging system. And then there is addition of the noise, which ruins the measurement, and in the end you end up having a distorted image which looks noisy, blurry, etc. So a typical solution to this is to solve an optimization problem, which many of you should be familiar with, when you sort of minimize the contribution of the noise, as opposed to trying naive methods where something like convolution theorem could be used. In the naive approach, you would actually take this convolution, and what you can do is you can reconsider the convolution from this mathematical operation, which becomes a product of two Fourier transforms, right? And instead of working in the image domain, it's natural to sort of tackle this problem in Fourier domain. However, in the presence of noise, the problem becomes really difficult, and you do need to solve optimization problem with the addition of your favorite regularization, so that this ill-posed problem actually becomes solvable, and you obtain some physically meaningful solution. But even if you don't dive into that mathematics too deeply, a natural question is to actually compare this to measurements. And yes, if you look in the Fourier space, you're going to be able to see exactly what's going on with the quality of these edges, and why is it that this representation of the image is so blurry, and what happened to the true scene. So if you look in the Fourier space, so for those of you who are not familiar, the majority of the information is centered around the central frequency. This is your k equals 0. And on the periphery of this space, you get the high frequency detail. So the high frequency is on the periphery, and the poor image, the inferior quality image, actually contains less of the high frequency information, which is the real problem. So if you were to quantify what's the actual difference between these two images, you might actually end up proposing a metric which would describe how many like high frequency components exist in the bad image, right? So and the question becomes, how do you recover that through SYN, given the Fourier decomposition of a particular SYN over this object or a SYN? The apparatus of understanding Fourier components in the image could actually be analyzed from the standpoint of physics. And this is a really nice experiment which people attending my course on computational imaging perform in class. You essentially take a lens, and then it has a Fourier plane, and then there is another lens. It turns out that an optical lens, just like the one that you have in your objective, in the camera and the camera lens, it turns out that the lens, the ideal lens, performs a Fourier transform. Essentially, what it does, if you remember high school, or maybe you took some classes on image formation of the physics of optics in your college years, maybe you remember that it actually collapses all of the information as a cone. And in the focal plane of the lens, you have a little spot which collapses all of the same information. It's exactly the same as the SYN on the left from your lens, but it's collapsed in a very low level representation. And you do see that same information in a condensed, so to say, manner. In the center, you would have a central frequency. On the periphery of this plane, you would have the high frequency components. And obviously, if you want to have a sharp imaging, you would want a lens that brings you that high frequency into the pupil, into the imaging system, so that the high frequency still enter the pupil of your lens. So if you play with this aperture, because you know that the cameras also contain those apertures, if you play with the aperture placed in the Fourier domain, you can visualize what you can also simulate digitally. Digitally, you can close that aperture, and this is a schematically shown representation where the image becomes very low quality, and sometimes you can't even discern what the object is on this thing, right? And you can see that in the closed aperture setting, you do get only the central frequency, and the periphery is black. If you open the iris just a little bit, you would still have the central contribution, but you would have more high frequency components. And essentially, you don't just pass the low pass operation. This is not just your low pass filter anymore, but you also start to pass medium frequencies. And whatever your pupil allows, you actually can continue opening that aperture until the detail on the image is sharp. And basically, you open it entirely. It means that all of the high frequency that your lens is capable of accepting, that all of those frequencies are in the sensor, and you can efficiently image the high detail. And so this is a bilingual lecture, so I'm speaking English, but in Russian, I always receive this question, what is a computational imaging in Russian? I still don't have a translation of that into Russian. It's вычислительные методы формирования изображений. So this means that it's a computational method that allows you to enhance whatever the pupil can accept into the imaging domain of your camera. So this is as far as your camera can go, this white circle, and by computational methods, you bring the higher frequencies into the resolvable or visualizable area, which is called numerical aperture of your lens. And all of that is done computationally. As you do that, and this is where we start seeing analogies between imaging physics and computational systems and computer vision, as you try to optimize those high frequencies, you would mostly be interested in a reconstruction. So if you're solving that optimization problem, probably the metric of interest, okay, you can take L1 or L2. Maybe L1 will give you a sharper image. Maybe you can add certain other metrics, such as structural similarity, just to, if you know the ground truth. But you will always be interested in performing a good quality reconstruction. You want to see sharp hair. You want to see, as we discussed, the highest frequencies possible. However, you obviously know the computer vision task, and perhaps all you're interested in is not at reconstruction, but also other metrics, such as the segmentation, example of which is shown here on the image on the right. For example, you want to segment this pair of ears in the dog, right? And you essentially, you need to provide that annotation. Okay, you perform your typical, you train your favorite model, such as UNet, and you manage to train, you show a bunch of such images, you manage to actually see the object of interest and segment it, localize it on the images. And the question that we actually asked in our group for the first time is, okay, let's find these optimal frequencies, not just for reconstruction. Let's forget how the image actually looks like, but let's talk about the quality of the target downstream task. If you want to perform segmentation, that's your target task. So what's the dice score? What's the perfect segmentation quality, depending on the frequency decomposition of your scene? What frequencies do you need for your object of interest? So this is the proposed layer that we proposed, and we called it GAFL, which stands for Global Adaptive Filtering Layer. What you do is you take that UNet or any other neural network that performs your target task. For example, it does segmentation, or it can do classification, denoising, whatever. And let's say you append the following construction just in front of that neural network. Essentially, this construction consists of two operations and a weight matrix, W. So the first operation actually performs the Fourier transform. Then you multiply by a matrix of coefficients, and then you do some normalization, but then you perform inverse Fourier transform. And that's that. Essentially, you appended a layer which goes into Fourier domain, multiplies that Fourier domain image by a matrix of coefficients, and then you enable training of this layer alongside the main architecture of the neural network. So this is probably the simplest, architectural diagram you would see. But the idea is that, yes, as your neural network, as you optimize your target function for performance, say, classification or any target metric, right? This matrix of coefficients gets also learned, and you actually iteratively from epoch to epoch, you essentially learn the matrix of coefficients, which becomes an optimal filter, and it's also global for the entire data set that finds the frequencies that are good for your image, given that the need to maximize the target metric for the entire data set. So these are some examples. If you perform your image net classification, like cats versus dogs, is a standard task. This is a Fourier transform, an amplitude of the Fourier transform for this cat. And then once you learn the coefficients, the amplitude spectrum looks a little bit better. So you actually learn those frequencies that maximize the classification. What's that? The F1 score for this classification task. So you now see that, okay, your classifier predicts that this is a cat with certainty, and you now know which frequencies are needed for that. And in image space, you can subtract. And if you played with these classifiers, you know that it's usually ears and eye area that boosts your, that actually the features that contribute to the classification accuracy are the ears and the eyes. And we can sort of observe that on this image. Yeah, so this essentially becomes something like a heat map as well for you to visualize which frequencies came into the decision for these different images that I'm showing. At the same time, you can see that structurally the image almost didn't lose anything, except that, yes, if you blow up, well, maybe, I don't know if Zoom allows you to see that, but this is your eye area. Essentially, the delta image accentuates the features that contribute to the classification task. In imaging, well, essentially, why is this interesting for natural images domain? It's a bit of a question, but there are multiple domains that could benefit from this, where you can where you're actually fighting for certain frequencies, essentially for every single high frequency that you can for your target task. One of such tasks is ultrasonic images, ultrasound, the medical ultrasound that you do in a hospital. One of the cheapest imaging modalities that actually allows you to look into the body. You can actually visualize organs and certain pathologies just using the ultrasonic imaging. And this is the result of learning the same frequency decomposition. This just Goffel layer proposes that the spectrum of your image should look like this if you want to perform a classification. For example, in this class, this is a normal thyroid, right? This is a thyroid gland, and this is a benign case of also thyroid neoformation. This is not a tumor, but it's a benign neoformation. So this is a foreign body to the organism. And essentially, you can see that classification. This is a basic encoder, which the baseline of the performance for classifying these two classes could be actually boosted a little bit to the top. So your accuracy becomes a little better. You can look at the confidence interval, so it's actually better. And you also see that the convergence to those optimal values becomes a little bit faster. If you perform segmentation, this, like in that example with the dog ears, right? Here it's also rather important. Well, we didn't have the annotation for the ears, but we do have annotation for this thyroid neoformations. And you essentially see that light architectures such as UNet get a significant boost to the performance of the model. So on the x-axis, this is your epoch. On the y-axis, this is your dice. And not only that, but also the faster convergence. And in case of heavy architectures such as DenseNet or ResNet, right? There are way more parameters there, and they learn the segmentation task better. But still, you can see that the Goffel allows you to learn and reach the plateau a little bit sooner. So here we show the results for that thyroid and also for the breast and the pathologist in the lungs. as well. So two famous little data sets for ultrasonic images. Other tasks such as denoising, erasing, amazingly, you also learn optimal frequencies for those tasks as well. So what's shown here in this middle row, for example, if you have an image of a dog and you just erase randomly a rectangle, a very popular model such as DNCNN tries to recover that. It actually tries to draw some features around the border, and it's a convolutional architecture, right? So it knows that, okay, in the vicinity of these pixels, I should probably draw the structure similar to the adjacent pixels. And that's actually the performance of this rather powerful denoising model, which is sometimes used for erasing. But because you're not just learning adjacent pixels, instead you actually learn the frequency decomposition. In our model, you can also visualize features. And once our model is at the bottom, you actually draw something meaningful. Even though there was no information in this image, in the erasing task, you were able to recover this portion, and you can actually see some of the fur of the dog, right? And like even here, you can see some low frequencies which existed here in the head of the cat, which we were able to recover, as opposed to DNCNN, which just has no idea what's going on inside of that rectangle. So this is our little proposal. If you have a neural network, obviously we're not trying to, propose a new segmentation or classification sort of model, not at all. But what we're proposing is, if you have that sort of model, consider appending this layer. And it turns out, if you learn the optimal frequencies for your task, you might as well, help your application. You will be able to recover the needed frequencies. That would optimize, the target task. Okay, this is one application which we consider, and since that works from the imaging physics, the natural question that we asked was, what else could be borrowed, right? If there are photography lovers in this audience, maybe you know that little experiment called bokeh. Essentially, if you take your camera, it's a professional camera like DSLR, where you can detach the lens, and where there is that lens, you can place a little aperture cut out of the cardboard, and that will become your factor that affects your point spread function. It affects the kernel that is responsible for the image formation. So in typical situation, this is something that looks like Gaussian, right? In ideal imaging system, it's probably a single pixel, right? It's an ideal imaging system, so you convolve with a central pixel. But over here, whatever the PSF and the imaging pupil function is for your imaging system, you actually encode some information into it. And this is a really nice experiment just to play. You don't need to know the word convolution to play with it, but you just cut that shape. And what you see is that every time you have that bokeh in the original image, in the shape of the actual aperture in your camera, you convolve that with that factor in PSF or factor in shape, and it helps you to draw hearts in the image. If you're into portraits, portrait photographers love this because, okay, you can create nice images for, I don't know, St. Valentine's Day, for example. But, okay, if your task is now to count these hearts, it becomes actually doable, and it brings us to the problem of, again, borrowing this imaging analogy into the world of computer vision. And here, let's consider this problem of segmentation for the bladder. bladder is like urine bladder is a hollow organ, which is typically visualized by same ultrasonic images or some more complex imaging modalities such as computed tomography or magnetic resonance imaging. The bladder here showed in yellow. Okay, if you just slice it, you will see something like these hearts. You will see that at different slices, you actually can recover the shape of the object. And this is, and if this is exactly the shape that you want to segment, perhaps you want to encode that information in the kernel, just like it happens here. So now, if you know this and can somehow learn that kernel, the segmentation becomes much easier because it occurs again by virtue of this convolution. Convolution operation with kernel will accentuate just the organ if you just perform this convolution of these two images, for example. Okay, it's a big question how to actually initialize shape into the kernel, and I'm not going to go into details here, but you can learn that either by using some separate units where a small, very little portion of ground truths is taken to learn this set of shapes, or you can take heat maps from the down sampled parts of this unit architecture. And after playing with several architectures, we actually found a hybrid model that allows you to take the heat maps into account using some attention models and some fitting of these coefficients. But then again, it sounds a little bit complicated, but all we're doing is we're actually fitting a shape of the segmentation mask into the object that you're trying to segment. So this is a data set for birds, and I'll show results for that in a moment as well. So for the MRI problem and for the problem of actually segmenting the wall of the bladder, you can see that architecture actually works really well. Sometimes you miss classes by conventional architectures altogether, whereas our model allows you to, extract the contours really well. Quantitatively and visually, the model, this hybrid model that actually repeats the shape of the pattern, actually becomes a new segmentation sort of for the bladder in MRI. Now, we also tried it on a different data set. And for this data set, we visualize the heat maps right before the output, that as it goes out of the model, you can sort of visualize it and compare it to the ground truth. These models with some deformable convolutions, attention unit, and all of them really struggle extracting some complicated cases, whereas our model actually, surpasses them. You can see it by virtue of dice coefficients and by virtue of just visually. As a segmentation mask, it becomes better. So this is the general theme, the general sort of apparatus that we're trying to implement in my group. And as already discussed here, you do want to see sharper images. And for those of you familiar with digital signal processing, you can either do it essentially frequency by frequency, or you can learn the impulse response function, which is what is directly relevant to this PSF measurement or the kernel measurement. So you can either learn by your networks, you can learn these operators, or you can learn what improves the target task in the images. Again, you have this freedom just selecting optimal frequencies or learning optimal shape for your problem. And in imaging, okay, today you probably will choose some transformer or some even diffusion model if you want to perform a segmentation task and reach that sort of level on benchmarks. We're not trying to compete with those powerful, really, really heavy models. We're trying to actually borrow the apparatus of efficient learning for your task of frequencies and the response functions for your downstream task. And again, in imaging, on natural images, it's probably somewhat, unjustified, you can say so, even though I love that something like that could be tried in computer vision. But in medical imaging, there is a really, really good use for that. So another problem that I wanted to describe today is actually magnetic resonance imaging. So if you need to take Fourier transform to recover your ideal image and to see how much of a frequency components you have in your natural image, in MRI, it happens that the entire apparatus measures them actually column by column or row by row, as it's shown on this image. So again, you would think that you are scanning your image that would look like this, but instead your detector measures K-space. So this is one of type of detectors which directly measures K-space, and actually you even lose some information as you do the Fourier transform in order to recover that optimal image in the image domain, right? So that radiologists or doctors would be able to look for pathologies and study that image. So the problem with such acquisition is that it takes really long time. For those of you who did MRI and maybe you were inside of that machine, you have to stay still for like roughly 20 minutes, and for some complicated workflows and sequences, you need to stay there for up to an hour. And you need to really lay motionless because you will introduce motion artifacts. Motion artifacts here are really special because they occur in K-space. So as you try to fill that Cartesian grid, you actually fill it, column by column, and there are encoding mechanisms that allow you to recover your frequency space completely by virtue of those magnetic field gradients. But if you happen to move your body part during one of those, filling one of these rows, you would immediately introduce motion artifacts exactly in that area of K-space, which would have adverse effect in the reconstruction as well. So if you ignore elastic deformations, you can model those motion artifacts as translations and rotations. And conventionally, of course, you have that measurement, you have the K-space. And conventionally, what you do is you actually iteratively perform rotation transform and translation transform, and then do inverse Fourier transform, and then perform your optimization. This is called like a baseline after autofocusing algorithm. This is the virtue of updating the image by iteratively. And it's done retrospectively, where you essentially learn the parameters of rotation transform, this theta and alpha, and translation transform until your optimization problem doesn't reach a plateau. So this is fine. It's a nice little method, and it's been used for many years, since 2000 probably. And you essentially find those trajectories in terms of parameters theta and alpha that allow you to receive the best image quality. And so instead of image like that, you get an image without the motion artifacts. So now a proposal, we added just a little bit prior information over here, where whatever you did in a baseline autofocusing, you also pass through another UNet. And this is just one example of architecture that could be used. But really what you're doing, you're multiplying, you're taking this output from in the image space, and you multiply it by the iterative output of the autofocusing, and then you perform your optimization. So this UNet essentially extracts additional prior information from the data and improves image, and actually enhances training stability and improves image for the overall optimization task. It turns out this becomes immediately, such a simple addition immediately becomes a new sort of method for improving your motion artifacts removal. So over here, you can see that even in the case of severe motion, some baseline models really produce some blurry effects. This is one of the models that also is based on autofocusing conventional optimization-based method. And this is a gun, obviously with the appearance of guns, people try to recover images by virtue of guns as well, and generative models. Unfortunately, they often draw some details, some unrealistic features, and radiologists immediately see those imperfections. If we perform our method, you don't just recover the image, but you also guarantee that that UNet serves just a little bit to the baseline autofocusing. Autofocusing will never draw something that didn't exist there, but it still has some artifacts from the motion. You can't completely get rid of the imperfect image quality over here. However, that little UNet prior adds, and you can see how good that image is. Well, it's also good if you look at metrics, and these are some values that show you that it's pretty much robust in terms of performing in a very good signal-to-noise ratio, but also it shows very good performance if you have a noisy measurement. For example, this image, when it's a low Tesla machine that has a lot of noise in the background, and it still recovers really nice anatomically feasible image. And by terms of metric, it's also a very good performance. We are showing here a structural similarity metric, but well, you probably know that it's not the best metric. Recently, we actually released the comparison of those metrics that just appeared. It's essentially image quality assessment for magnetic resonance imaging, and my students also performed a very vast implementation of, I think there are over 40 metrics today that you would typically consider for computer vision. So consider this article if you're interested in the image quality, but as everyone who published papers recently know, you need to show the structural similarity, and that's why we showed it. Okay, it's accepted to MICAI, and yes, if you're interested, here is some realization, and you can read the full paper here as well. Okay, so we can remove the motion artifacts by harnessing Fourier space. But a natural question is also, what else can we do with this Fourier space? Okay, in MRI machine, you don't get images, but instead you get this column by column measurement, and it takes half an hour to get that measurement. What can you do to accelerate that? And now we step to the discipline of compressed sensing, which is a simple idea that, okay, if you need to collect all of that information, let's not do that at every frequency. Perhaps we can do that at skipping every other line, for example, and maybe sample some more frequency in the central frequency part, because the majority of information, as we discussed in the first part, is contained within that area. Well, if you take an image like that and just basically delete synthetically every other measurement and perform a standard reconstruction, you will see aliasing effect. You will see, the overlaid information, which is essentially the contribution in the central frequency. You can still guess that this is a knee, but it's repeated multiple times because you have that periodic sign-like patterns in the Fourier domain along the x direction, right? So the compressed sensing is traditionally concerned with recovery of that image. You take the incompletely filled k-space, and you really need to come up with some idea that some model that takes this and recovers this as opposed to aliased image. This is a really old problem, but again, it's in a really big boost of interest from the deep learning community recently, which is pretty much explained by two reasons. The first reason is, okay, this is a nice problem where you have k-space and where deep learning community can actually play with the data set. And the other reason is this huge challenge released by Facebook called FastMRI, where they released, in collaboration with several hospitals, they actually released a large data set containing raw measurements for performing reconstruction of the anatomic images. And then they also provided several basically scripts that generate undersampling masks. And there were a number of challenges and competitions where people would compete to recover this image with the best possible image quality. And again, just for the eyeball of your estimation, if you just take 1/4 of the k-space, it allows you to, basically accelerate your scan from 30 minutes to 7 minutes. And you will not get, if you just do that, you will not get the quality of an anatomic detail in the reconstruction, but you will get something blurry like on this image. But perhaps that would be still useful for the radiologist, for example. And this is again where we come in my group. By the way, my PhD student, Sergei Kostrurin, is one of the contributors to the model that won that challenge. And since then, we were actually considering other opportunities for improving the pathology localization on such images. So let me briefly describe that. I will pretty much describe the general medical vision workflow, and that is like that. Okay, you first obtain that k-space image, right? And typically you want to do undersampling to accelerate that. Essentially, you take that, just like we described just now, okay, you take the sparse sampling approach and don't resolve every frequency, and you do your inverse Fourier transform and recover the image that looks blurry. Then you do a reconstruction. This is your typical, you optimize structural similarity typically, and you want to get a nice quality image space image so that radiologists could use it. And then the next step is you actually do the medical vision task. You essentially localize the pathology. Okay, there is a problem on the knee over here, and this bounding box shows where exactly that occurs. So these three steps we actually proposed this year to replace with just one step where you undersample for the ultimate task right away. So if you're no longer interested in the quality of the image, but if you're recovering for the quality of pathology localization, this becomes your target metric of interest. Okay, so the way we do that is, again, iteratively, you just take a blank k-space, and then you essentially take an image, take inverse Fourier transform, multiply by that blank image of coefficients, do inverse Fourier transform, and then keep improving this mask in sort of solving this optimization task using the gradient of the loss. And the loss could be really any function that you want to optimize in your problem. Typically, everyone is interested in structural similarity here. Okay, if you want to do dice, take your dice. Basically, this is your model, a ground truth, and this is your loss that will help you find the optimal undersampling pattern omega, which is essentially a set of lines like this, and that will allow you to maximize quality of the reconstruction exactly where you need to. The image will look bad, but the quality of localization will be good. That's the key idea. So this is the segmentation result. And essentially, okay, it's a bit of a complex slide, but you can see three classes of the image over here in the fully sample case space. And essentially, if you accelerate it 16 times, your image becomes completely ruined. So if you take those fast MRI masks, you wouldn't be able to localize these regions very well. Actually, the models show very low dice scores, right, for these classes. In our case, even though the image looks bad, you can still boost the quality of the segmentation as it's shown in this metrics, right? This is a sort of aggregate of this study where on one axis we show the overall quality of reconstruction, and on the y-axis we show the quality of segmentation, right? And all of the models, they actually sort of fall on this line, which tells you that, okay, if you take really large acceleration factors, your image is gonna look very bad. Your structural similarity will be very low, and that means that your segmentation will be very poor. You will not be able to see the segmentation very well. And if you do our trick with the optimization of the undersampling mask, we tried two different optimization methods for that. You can see that even though this structural similarity at really extreme acceleration factors is pretty bad, you're still able to get a really nice, compared to the baseline, really nice segmentation quality. This is just some example for annotated fast MRI dataset for the knee dataset. And again, in these bounding boxes, you can see better reconstruction detail for this particular case, as opposed to boosting how entire image looks like. So yeah, we also, obviously, since you do segmentation and reconstruction, you can also do classification. So your question becomes, okay, if there is a tumor in the image, right, and you want to detect it, typically you would need to spend like 1 hour in the scanner, and then you need to be, that image needs to be analyzed, et cetera, et cetera. In our undersampling approach, you would take a sparse sampling. You learn the optimal mask that just maximizes the classification score for this particular region. Yes, that works pretty well, and this is one of the stunning results for the BRATS dataset. It's another challenge dataset that's used for detecting tumors in the brain MRI. You can see that for the fully sampled case, essentially tumor is really well classified because it's an easy, simple classification problem. However, if you do the acceleration task 16-fold, that becomes a very complex classification problem. Essentially, this little white blob is no longer detectable. You can't classify it, right, well enough. So that's a F1 score, which you can boost back to almost 0.9 by using our undersampling mask. Essentially, choosing the right frequency allows you to return the F1 score back to the baseline of a fully sampled case space, but your patients would need to spend 16 times less time in the scanner. So this paradigm, again, is well documented. Please read the full paper if you're interested. And we actually followed up, and there was another challenge where similar methodology is starting to appear. Essentially, people are interested in finding the optimal undersampling patterns, optimal frequency decomposition that would boost your target task. So it was a challenge where, again, our team is one of the winners, and it's published in this paper. Yeah, this is all I have to discuss today. This is the team, who performed a lot of this work, and I want to thank all of them. And basically, this is a bit outdated, but yeah, we're an active group, actively publishing in computer vision, medical vision domain. So if any of that is interesting to you, please contact me. I am always happy to find collaborations, and welcome to our laboratory if you're at Skoltech. That's another invitation. So this is all I have. Yes. Thank you.
Dmitry, thank you very much. Now we have some time for questions. Are there any? So maybe I can start. Could you go back to the slide 13?
Over here.
Yeah. So this is maybe a naive question. So in this algorithm that you use in the point number 3, yeah. So what you basically do, you take the Fourier image, and then you so this multiplication is an element-wise multiplication, right?
Yes, it's an element-wise multiplication. Yep.
And there is probably and this is this motivated sort of by the discrete convolution theorem, where in the Fourier domain you also have to element-wise multiplication, and does it make sense to consider some more general operation here?
It's a very good question. Yes, there are neural operators that you can learn instead of doing it like this. Basically here, because we wanted not just, so basically we wanted to see this pixel-wise operation. We want to learn this matrix omega and then visualize an optimal filter for every picture. Perhaps you would be able to recover that in the proposed case, but this would be just a little bit more complex for the interpretation and visualizing what's going on with each particular frequency. But you're right. That's another way of doing that. Obviously, you are already in Fourier domain, so why not consider, the bulk operation as an operator?
Okay, I see. And regarding this last part where you sampled some, taking some subsample from the Fourier domain of the MRI image, is something like this actually used in practice? So is it like doctor can offer you to wait less, but maybe like cheaper price or something like this?
Yes, so it is being used as we speak, but it's starting to get more and more accepted in the medical community. But because at first, obviously, doctors were reluctant to accept any poor quality, because it's natural to expect the nice quality of a scan to make some vital decision. So if you want to see some fine pathology, this method is still not very good. Like, for example, you actually want to see, what's going on anatomically in some part of the brain, because doctors can make connections from anatomical structures nearby of this new formation. However, there is a whole set of other applications, such as, for example, radiation planning. Essentially, you know that, okay, there is there is tumor, and then you need to plan radiation treatment for this patient. It's like something like a chemotherapy or bombarding this area in this big machine. It's actually like a big application where they try to rescue patients, right? So in that case, you're not really interested in learning the fine detail in the image. However, you want to localize, you want to know exactly in which part you need to direct that radiation. So for radiation planning, this is a really nice application. And these methods of classical compressed sensing are being used. And deep learning is actually is starting to be implemented and even approved as we speak. So FDA approved one of the deep learning engines. Again, there are really large validation studies because, as I showed in that aliasing example, your deep learning model, is really prone to drawing something that's not there. And this is the application where it's not an ear of a dog. This every feature actually means something for a radiologist. So you want to be very careful there, and that's why there is this. This is a hindering factor, but thankfully so.
I see. And is it the only option to skip the lines, or can you do some of the lines with less resolution or something like this?
Yeah, so the question you're asking is essentially the same question that we're asking. Like, for example, you just mentioned resolution, and we say, okay, put your resolution metric here and learn what is the optimal, spacing between these lines. Like, for example, we learned this mask for segmentation, right? We want to segment well, but you want to resolve something. So you're welcome to insert the metric of interest. So this is essentially a new paradigm for doing what you want in K-space.
I see. Okay, so are there more questions? Yes, there is a raised hand, as far as I can see, or wait, what was this notification?
I have a question.
Yeah, please.
I must have missed it, but in your work about the kernels that resemble the objects on a segmentation task, are they fully learnable?
So as I understood the question, if you can learn the shape and make it a kernel, right?
It's like, do you kind of induce this information into the model, or it learns it?
Yes. So this is exactly our attempt. We try to predict the shape of the kernel by using whatever is available in your main architecture. For example, you can take the first heat map, or you can take the last heat map, which will resemble the shape of the predicted object, and then use attention between the adjacent heat map. We tried all of those sort of methods because how would you extract it from the architecture? Like take typical UNet, how would you actually extract it from there? And so we've tried these two methods, and we also tried learning it separately by introducing a separate little UNet, that we call the tiny UNet, where you can learn the shape of kernel, which you then move to the main UNet now that you know the shape of the object.
Thank you.
Thank you. Are there more questions? All right, so if it is not the case, then thank you very much, Dmitry, again, for the very nice talk. Thank you.
Thank you. Thank you for inviting.
Yes. Yeah.
Have a good day.
You too. Bye.